Now we have two much more complicated equations to have to balance. These involve redox reactions, and we've got oxidation number changes that are not just ones and twos, so that makes them a little more difficult to work out by the method of just going backwards and forwards with elements. Things that I would look at when I'm looking at this is my common elements like oxygen, hydrogen and sodium. These have very common oxidation states of -2, +1 and +1 when they're in a compound. They don't, on the whole, have other oxidation states in the sorts of examples that we're going to be looking at here. The only oxidation state they would have is when they were an element, and they would have an oxidation state of 0. Therefore, a quick check across here says I don't have any elemental sodium or hydrogen or oxygen, therefore I haven't got a change in oxidation state of any of those elements here. The other key one perhaps for oxygen might be a peroxide, and I don't have any peroxides here. So this comes with experience, knowing those sorts of things. But having decided them, that leaves me with the only other element to deal with here is chlorine. So looking here, my chlorine starts in an oxidation state of 0 and it goes to +5. Yeah? So here we've lost 5 electrons. Also, a chlorine goes from here to here and it goes to -1. So here it has gained 1 electron. Now, if these two processes are occurring at the same time in the same equation, then this requires 5 electrons. You will need 5 lots of this to satisfy that 5 electron requirement of this chlorine here. So that means that we can times this by 5 up here, so that we satisfy the requirement that 5 of them need to change for every one of those. Now we can finish balancing the rest of the equation without too much of a problem. We can see, to start with, if we stick with chlorines, we've got 5, 6, so therefore we need a 3 there. We can now say our chlorines are balanced. We can look at sodiums next. We've got 5, 6, so we can put 6 there, and we know our sodiums are balanced. Next thing to look at is perhaps the hydrogen, because it's only here, and we've got 6 of them here and 2 of them here, so therefore we would need 3 waters to get that to balance. So my hydrogens are balanced. Left over is oxygen. I've got 6 here, and on this side I've got 3 and another 3, so therefore I know I'm completely balanced at this stage. The one below with antimony is a similar style of one. Again, we have no elemental oxygen or hydrogen. We've got no peroxide around, so therefore we can ignore our hydrogens and oxygens in terms of oxidation states and leave them to the end. The antimony then. The antimony, we have 2 here, so we need to put a 2 here so that they balance. Each of these antimonies starts at 0, and each one goes up to +5. So we have 2 of these doing that. So we have a 10 electron process happening there. Yeah, this needs to lose 10 electrons to go from there to there. The other element to look at, which is not hydrogen or oxygen, is my nitrogen. It is starting over here as a +5, and it is over here, it is ending as a +4. So this is a 1 electron process. This is gaining 1 electron to go across there. So if I've got 10 electrons down here and 1 here, I'm going to have to make all of these down here have enough electrons to do that, I'm going to need 10 of these. So I'm going to pop a 10 there, and I'm going to pop a 10 there. So you can see quite instantly we get to very unfamiliar numbers in these ones, and that's why they're difficult to balance by other methods. Having decided then that my antimonies are balanced and my nitrogens are balanced, let's take a look at the hydrogens next. So I've got 10 hydrogens here, so I will need 5 waters there to balance those. So my hydrogens are balanced. And hopefully, with only one thing to go, we are balanced on the oxygens now. So we have 30 oxygens there. We have 5, 10, 20. We've got the right number of oxygens on that one. And you can see with the numbers involved, that would be very difficult to balance by a different method.